we're going to look at more group definitions, and let's call this definition here. So suppose G with a binary operation is a group. Then the number of elements in the group is called the order of the group. And is denoted by, say, the double bars like this. And then, of course, if there's a finite number of elements, then the group is called a finite group. If it's infinite, then the group is called infinite. Another definition that we have is of an abelian group. A group is called abelian if all of its members commute under the group's binary operation. i.e., A star B equals B star A for all A and B in the group. So for all elements in the group, they commute under its operation. If that's true, the group is called an abelian group. Another definition we have is called a subgroup. Suppose the set H is the subset of the group G, or of a group G, may be a better way to state that. and H itself is a group, under that same binary operation, is G, then H is called a subgroup of G. So in summary, what this is saying is that if H is a subset of a group G, and H is on its own terms also a subgroup under that same operation, then H is called a subgroup of G. So for something to be a subgroup of G, it has to be a subset of the original set, and it has to be a group under the same operation. Now we want to talk about subgroup tests. People have developed several ways to determine if a set is a subgroup, and they've developed these subgroup tests. And there are several different ones that they've developed. And here's one I want to look at. And this is actually a theorem. Suppose H is a non-empty subset of a group G, then G is a subgroup excuse me, then H is a subgroup of G if and only if for all A and B in H, we have A, B inverse is in H. This is one of the most concise subgroup tests that there is. And so again, what this is saying is if you have a subset of a group G, then H is a subgroup if for every element in H, we have that H with binary operation, B, A with binary operation, B inverse is in H. And if this is true, then you'll have a subgroup. Now, the advantage of this is that if you know that something's a subset of a group, then you only need to do this simple test to prove that, in fact, that your set H is a subgroup. So let's try to prove this. I'll prove it mainly in the one direction. I'll prove that if we have for all A and B and H, we have that this is true. We'll prove that. So that basically shows that we can use the subgroup test. So let's do the proof. again, we're going to suppose for all A and B in H, we have A, B inverse in H. So suppose we have that. And so let's try to show each of the things. Let's start with identity. We remember if something's a group, it has to have an identity. So we'll show that this implies that we have an identity. So let's start with that. So let A be in H. Let's say it's an element in H. So of course that means then we can write that this way. This seems kind of odd to say it this way. So then if A is in H, we can say state this way, just repeating ourselves. But the reason we want to do this is because we say A and A is in it or in H, then we can say that A star inverse A is in H. And of course, this is what? This is precisely the identity. So therefore, the identity is in H. So we took any typical element and said, you know, it's in there. And based on our assumption here, for all A and B and H, we have this is an H, so we just took A here, and then the inverse here, and that's in H by our assumption. And then this is the identity. The identity's in H. Next, let's check the inverse. Let's say B and H. Then from above, we know that the identity is in H. We just proved that. So we have B and H, and the identity is in H. So we have, if we have those two in H, and let me rewrite this just in a little bit better order, just so we can see we have. It really doesn't matter which way you write it, but let me just for emphasis, let me write it this way. So we know that the identities in H, no B's in H. Now, according to our assumption here, if these two are in H, then up here we have E star B inverse is in H, like this. And of course, that means, therefore, because of course this is going to be B inverse, therefore B inverse is in H. Finally, closure. Remember, for closure, we have to pick any two elements in H and prove that they're product is in H. So let A, B be in H. Now we know from above, from the last step, we know B inverse is in H from this step right above. And then also, we know that, so we have up here that A and B are in H. And so what would be a good way to say this? We can say now, let me say it this way. So A and B inverse are in H. Can we just showed A is in H, B inverse in H? And then by our assumption up here, if these two are in H, A inverse B is in H, but of course, then A star B inverse is in H, like that. In other words, I'm just using this up here. If these two are in, then these two are in. And of course, what does this mean? This means B inverse just gives us B back, huh? So A star B is in H. So we start out with two typical elements in H and prove that their product or whatever this binary operation is gives it in H. Now for associativity, it always comes along from the group, because we're not doing anything different. We're using the same elements. If the elements they're in a subgroup were associative in the group, then they're certainly going to also be associative in the subgroup. So this comes from the group. So we don't need to check that. But we just proved then the subgroup that if A and B are in H, then if we have A star B inverse in H, then we have a subgroup. So this is all we need to do to show something's a subgroup if we have a subset of a group. So let's take a look at this problem. Use the subgroup test to prove that 5 times the integers, which is the set that looks something like this, -15, -10, -5, 0, 5, 10, 15, and on, is a subgroup under addition. So we're going to try to prove this. So now notice that Z, which is the integers, under addition is a group. And this 5Z is obviously a subset So we have the one condition that the original group is a group. Remember, before we proved that this was a group, and now 5z is a subset of z because it's just the every fifth integer. So that's a subset. So now, and then notice the typical element will be like 5 times some integer, huh? And so we want to use the subgroup test. We need to show that for every element, and let's look back at that, for all A and B in the subset, we have A star inverse B is in that subset. So let's see if we can apply that here. So let A and B be in our subset 5Z. Now, what does this mean? Of course, what would A have the form? A would have the form, so A is going to be equal to 5n, where n is some integer, and B is equal to 5m, for some integers m and n. So that's the form that they would take if they're in Z. And now we have to show that A plus B inverse is in 5Z. Remember, that's the requirement for our test. We have to show that A with our star, in our case, the star is addition, plus B inverse is in Z. And now what is B inverse? Of course, if this is B, what do we have to add to this to get our identity? What do we have to add to this to get 0? And of course, that's going to be negative 5m. So note B inverse is going to be negative 5m, because if we add B to B inverse, we get the identity 0. So now we have to show that A plus B inverse, we have to show that that's going to be in Z. And of course, what is that? A was of the form 5n, and then B was of the form, excuse me, B inverse was, say, negative 5m. And so this is going to be 5n minus 5m, 5n minus m. And now these are two integers. The difference of two integers is going to be an integer. So when we do A plus B inverse, we get 5 times the integer, and that's a typical element in the set. So that means that's in our set 5Z. So by the subgroup test, five Z is a subgroup of Z. So now let's consider this. Now, for this next problem, remember that if something's a subgroup, say a set with a binary operation is a subgroup, then going in the other direction, it must satisfy the subgroup test. Now we're going to use that fact in this next problem. Say, suppose H and K are subgroups of G. So we've already, however, they've already established that these two are subgroups. Prove that H intersection K, again, we're assuming under the same binary operation, but a lot of times they'll just say this, but technically what it really means is this, the intersection of H and K under the same binary operation as G is a subgroup of G. So let's try to prove this. So remember, we have to pick two typical elements in here and prove, we've picked, say, an A and B in here and prove that AB inverse is in this set. So let's take a look at this. So we'll start with this let A and B be in H intersection K. And then what does this mean? So now when you start with something like that, then a lot of times it's right with what you know about this. So for example, if we know that A and B are in H intersection K, again, because of the intersection, then we know that A and B are in H, and because it's an intersection, and we know that A and B are in K. But since A, excuse me, since H and K are subgroups, we know, again, since they're subgroups, then we know that for any A and B in H, we have A star B inverse to be in H, because this is a subgroup over here. And we also know that A star B inverse K is in K, like that. We know that because we're told that H and K are subgroups, and therefore they obey the subgroup test. So we started here. We determine A and B were in each of those. Therefore, we know that this is true since they're subgroups. And then, so now what does this mean? This means then, since this is in H and this is in K, then that's in the intersection HK, like this. And now see what we've done. We picked some two typical elements in H intersection K and proved that A star B inverse was in that intersection. Therefore, H intersection K is a subgroup by the subgroup test. And next, let's take a look at this problem. suppose that G with some binary operation is an abelian group, then for all A and B in G and all integers N, we have AB to the N equals AN BN. So let's take a look at this. So again, remember for an abelian group, all the members of the group commute. So let's see if we can do that. We'll probably do this by induction. And let's actually say this is for all integers. This should actually be greater than or equal to 0, like that. And we're going to prove this by induction. Again, I'm going to limit it to values n greater than or equal to 0. And so again, by induction, let's do the base step or basis step. This would be for n equals 0. For n equals 0, we'd have ab to the 0. The question is that going to be equal to a to the 0, b to the 0? Of course, this is 1. This is 1 times 1. So this is 1 equal 1. Yes, that's true. Then the induction step. Remember, in the induction step, we're allowed to assume it's true for n. And then we want to prove that it's true for n plus 1. So we're assuming it's true for n. And if we can show that if it's true for n plus 1, then we're done. And so now in this case, maybe we want to just start with this. Let's start with our assumption and see if we get to, so again, what do we want to show? Want to show, it's always good to keep that in the back of our mind. We want to show AB to the n plus 1 is equal to A to the n plus 1, B to the n plus 1 is what we're actually trying to show. Let's sort of keep that in the back of our mind. I think this time we can start with our assumption and work with it. So let's multiply on the left by AB. So we'll go AB on the left here, AB equal AB on the left here, A and B. So all I did was multiply by AB on the left. Now, of course, right here, and excuse me, there should be an N right here, and there should be an N here. And now when we multiply this together, of course, we're going to get AB and plus 1. And now over here, we have, now one thing to remember, because it's an abelian group, we can commute these, so we can switch the order of these. So this is BA, A-N, B-N, like that. Or actually, I think I did that the wrong way. I should have switched the middle two. So let me go through all the steps. This would be A, B, A-N, B-N. Again, let's flip those middle two. That'll be A-N, B, B-N, like this. Again, we're allowed to because it's an abelian group. Let's just note that. Abelian group. And the members are commute. So we flipped the order of these two. And then, of course, here we're going to get A, B, and plus 1. This is going to be A and plus 1, B and plus 1, which is what we're trying to show. So by induction, we showed the base step worked. And then the induction step, we assumed it was true for n. And we wanted to show that it was true for n plus 1, which is what we did. So true by induction.